In this video, we'll begin our exploration of classification tasks in machine learning. Instead of building models for quantitative outcomes, we'll build models for categorical outcomes. A classic tool for modeling binary responses is logistic regression. Why do we need special models for categorical variables? Suppose that we're hoping to model a medical outcome that has three possibilities: infection with bacteria type 1, 2, or 3. What if we tried to turn this into a situation where we could use linear regression for modeling? We need to turn medical condition from a categorical variable to a quantitative variable. Let's say that we did this by assigning the numbers 1 to 3 for the three types of bacteria. One problem with this is that this labeling implies an ordering to the three types of infection. With this particular ordering, we've implied that infection 2 is more severe than 1, and that infection 3 is more severe than both 1 and 2. Another problem is that even if 1 is the least severe and 3 is the most severe, the exactly 1 unit difference between outcomes doesn't necessarily make a lot of sense. No matter what numbers we assign for the three conditions, we'll face problems like this when trying to use linear regression. This is why we need tools that are suited specifically for categorical outcome variables. Logistic regression is a technique that is used to model binary response variables, for example, success or failure, or presence or absence of a condition. Success or presence of a condition generally is represented by y equals 1, and failure or absence is represented by y equals 0. In logistic regression, we model a special quantity, the natural logarithm of the odds of the y equals 1 event, which is also called the log odds. The odds of the y equals 1 event is the probability of the event happening divided by 1 minus that probability. In logistic regression, we model the log odds of an event as a linear combination of the predictors, just like how in linear regression we model the average or expected value of a quantitative outcome with a linear combination of the predictors. Let's look at an example. We have data on the financial and personal characteristics of several individuals and whether or not they defaulted on a loan. We're interested in modeling the chances of defaulting as a function of credit card balance, and this is expressed by the logistic regression model shown here. When we fit this model, we get estimates of negative 10.65 and 0.0055 for beta 0 and beta 1. Let's go over what these numbers mean. The intercept beta 0 is interpreted as a baseline log odds, the log odds of defaulting when all predictors are 0. So the log odds of defaulting when credit card balance is $0 is negative 10.65. This means that the odds of defaulting is e to the negative 10.65. Because odds and probabilities are related by simple formulas, we can convert this odds to a probability. The probability of an individual defaulting on their loan, given a credit card balance of $0, is quite small, 2.37 times 10 to the negative fifth. Note that we should be cautious when interpreting intercepts because sometimes setting all predictors to 0 is senseless. Here, a credit card balance of $0 is realistic, but for quantitative predictors such as height and weight, 0 values make no sense. In those situations, interpreting the intercept amounts to extrapolation. Let's interpret the beta 1 coefficient. The beta 1 coefficient is interpreted as a change, a difference in log odds, which is algebraically equivalent to the logarithm of an odds ratio. To see why, let's use our general model formula to predict the log odds of defaulting for two cases who differ in their credit card balance by $1. We see that the difference in these two predicted log odds is equal to beta 1. A difference in logs is equal to the log of the ratio, so this is why beta 1 is interpreted as the natural logarithm of an odds ratio. We can interpret this coefficient on a more natural scale by exponentiating. While beta 1 represents the natural logarithm of an odds ratio, e to the beta 1 represents an odds ratio. The two odds being compared in this odds ratio are the odds of defaulting for two cases who differ by $1 in their credit card balance. The fact that the beta 1 coefficient is positive and the odds ratio is greater than 1 indicates that as credit card balance increases, the probability, odds, and log odds of defaulting on a loan increase. Let's look at another example where we model the log odds of defaulting as a function of both credit card balance and whether or not the individual is a student. Student yes is an indicator variable that is 1 if the individual is a student and 0 if not. When we fit this model, we get the estimated logistic regression model formula at the bottom. The intercept is still interpreted as a baseline log odds when all predictor variables in the model have a value of 0. So negative 10.75 is this baseline log odds of defaulting for a non-student with a credit card balance of $0. We can convert log odds to odds and then to probability as before. The probability of such an individual defaulting on a loan is very low. The coefficient on balance, beta 1, will be interpreted as a log odds ratio, as in our previous example. But with the inclusion of the student variable, the interpretation will change slightly, as is the case for linear regression models with multiple predictors. So let's compare two cases whose credit card balances differ by $1, but who are otherwise the same. Let's say that they're both students. We can predict the log odds of defaulting for these two cases, and we see that the difference in these log odds is the beta 1 coefficient. We would see the same result if both cases were non-students. So, beta 1 is interpreted as a log odds ratio, holding constant student status, or among people of the same student status. In the context of our actual numbers, e to the beta 1 represents an odds ratio, and we can interpret the odds ratio of 1.0057 contextually as follows. Among people with the same status as being a student, or as being a non-student, in other words, holding constant student status, each $1 increase in credit card balance multiplies the odds of defaulting by 1.0057. Another way to phrase this is to say, holding constant student status, each $1 increase in credit card balance is associated with a 1.0057 multiplicative change in the odds of defaulting. We can use a similar process to determine the interpretation of the beta 2 coefficient. We see that beta 2 is a log odds ratio comparing a student to a non-student, but who have identical credit card balance. Using our estimates from the model, we see that the odds ratio is 0.489, which we can interpret as follows. Among people with the same credit card balance, holding credit card balance fixed, students have 0.489 times the odds of defaulting than non-students. That is, for a fixed credit card balance, students are less likely to default than non-students. So we focused on interpreting coefficients in logistic regression models so far, but now let's take a look at how we can use this model to make hard predictions about whether someone will default on their loan. Let's say that some new individual has a credit card balance of $1,900 and is not a student. We can predict their log odds of defaulting directly from the model, and from there, the odds and probability of defaulting. This predicted probability is known as a soft prediction. It is a quantitative form of a prediction for this individual, but we have not yet made a hard call as to whether or not this person will default. We can make a hard prediction, a direct guess for the outcome, by thresholding the predicted probability. A natural threshold for probabilities is 0.5 because when a probability is greater than 0.5, the odds are greater than 1, and the event is more likely to happen than not. So we'll use the following probability classification rule. If the predicted probability is greater than or equal to 0.5, will predict yes for the lone default outcome, and if the probability is less than 0.5, we'll predict no. In this case, we predict that this individual will default. Let's look at one more example. This second person has the same credit card balance as the first, but is a student. We see from the negative coefficient for student that being a student makes an individual less likely to default, holding constant credit card balance. As expected, the predicted probability of defaulting is about 0.35, much lower than for person 1. Because this predicted probability is less than our threshold of 0.5, we'll predict that this person will not default. So, what we've done for these two hypothetical people is use our logistic regression model to predict a probability of the outcome of interest happening, a soft prediction, and then thresholding that predicted probability to make a hard prediction about the outcome happening or not. So, in summary, we've seen how logistic regression is useful for binary classification problems. Like linear regression models, logistic regression models can be used to describe relationships between an outcome and predictors if we look at coefficient interpretations. In particular, exponentiated versions of non-intercept coefficients capture these relationships in the form of odds ratios. We've also seen how to use logistic regression models for prediction. We can make soft predictions, predictions of the probability of the y equals 1 event, directly from the model by predicting log odds and then converting to probabilities. We can then threshold the probability predictions to make hard predictions. The same major ideas that we introduced in our regression unit still apply to logistic regression and other classification methods that we'll explore. Overfitting, the bias variance trade-off, and using methods like cross-validation for estimating test performance of models.